Good morning, dear students. I am Dr. N.M. Ganesan, Associate Professor, Department of Physics, Erode Sengundar Engineering College. In this session, I like to share some informations about superconductor and applications of superconductor, types of superconductor. Before to see, I like to share with you regarding the conductor, superconductor, and insulator. What are conductors? Suppose if I shoot a questions like that, your answer will be either nickel, iron, cobalt, aluminium, silver. Your answer may be correct. Suppose if I ask further questions that among these conductor, which one is the best conductor? How will you give answer? In that case, you can give the answer by checking them number of free electrons or number of valence electrons, not counting the total number of electrons. The total number of electrons will not determine the conductivity of a conductor. Only free electrons or valence electrons alone decides the conductivity of a conductor. Then what are conductors? Anything that conduct electricity as well as heat energy easily from one place to another place are called conductors. Okay, we shall come to superconductors. What are superconductors? Indium, lanthanum, mercury, vanadium, niobium, these are all the superconductors. Then what are the difference between the superconductors and normal conductors? Normal conductor ever act as a insulator. Even if you bring in the normal conductor like silver, gold, aluminium to very low temperature, it will act as a conductor. Even at very high temperature, it will act as a conductor. But the superconductors like indium, lanthanum, mercury, tantalum, vanadium, these will act as a superconductor only at a very low temperature. For example, if niobium is taken, its transition temperature is around 9.5 Kelvin. In the case of mercury, it will act as a superconductor below 4.2 Kelvin. If we raise the temperatures above that one means it will immediately come to the normal conductor. That is the difference. And the conductor, normal conductor like silver, aluminum, cobalt, iron, nickel, these will have some resistance. These resistance are not cancelled even the temperature is low or the temperature is high. But in superconductor there is no resistance to the flow of electricity. That means flow of current. This is the basic difference. In a single statement we can say that the resistivity ever disappear in the case of conductor, but in the case of superconductor the resistance is completely zero. Okay, shall we pass to the next slide? Yeah. In this slide, the topic that I am going to covered or given. The first one is type 1 superconductor. We know something about superconductor, that is a superconductor is a conductor, it does not give any resistance to the flow of electricity. Further, the superconductor is classified as a type 1 superconductor and type 2 superconductor. After that, once we are familiar with this type 1 and type 2 superconductor, we have to analyze that. And that means we have to find the difference between type 1 and type 2 superconductors. Still further, the superconductors are classified on the basis of transition temperature. The transition temperature is nothing but a temperature at which a superconductor loses its resistivity completely. Once we discovered the superconductor or any things, we have to use or bring it for application purposes. By the way, we are going to see some applications like SQUD, bullet trains, cryotrons, and so on. We shall see one by one in the next slides. Same. In this graph, the type 1 superconductor is explained. The x-axis shows the variations of magnetizing field. Y-axis shows the variations of magnetic moment in the negative direction. For example, if you take the niobium, the transition temperature is 9.5 Kelvin. Suppose if you maintain a temperature around 8 Kelvin means the niobium will act as a superconductor. My next question is that even if the niobium is maintained in the temperature less than the transition temperature, the transition temperature for niobium is 9.5 already said, but you are maintaining a temperature 8 Kelvin. Now the niobium is in superconducting state. Can you cancel the superconducting state of the niobium? Yes. By using magnetic field as well as by increasing temperature, we can cancel the superconducting property of the niobium. But condition is that you shouldn't alter the temperatures. And then how can you cancel the superconducting property of niobium? Next chance is only the magnetizing field. I will try to apply the magnetizing field on the niobium using artificial magnet, that means electromagnet. By increasing the current, the magnetizing field also increasing, the magnetizing field applied to the niobium also increasing. As H increases, what is happening in the niobium means the magnetic moment increases little bit slowly in the negative directions. The sloping line shows that as magnetizing field increases, magnetic moment also increases in the negative direction. It is true up to critical magnetic field mentioned as Hc. Once the applied magnetic field reaches the critical magnetic field, immediately the magnetic moment penetrations come in positive direction. That is, all the magnetic flux suddenly entered into the niobium. As a result, the niobium became a normal conductor. In this case, you can see only two regions. One is superconducting region and another one is normal conducting region. Suppose if you want to know example for some type 1 superconductors are aluminum, lead, mercury, tin, lanthanum, and so on. This slide shows you that the variations of magnetic moment with respect to magnetizing field. The type 2 superconductor is one in which the material loses the magnetization gradually rather than suddenly. It takes place in the first case, that is in the type 1 case, the penetrations of magnetic flux is sudden. Here not like that, the penetration is gradually entered. The magnetization curve for the type 2 superconductor is shown for your understanding. I would like to explain further. See, in the x-axis we are taking the magnetizing field, in the y-axis we are mentioning the magnetic moment. We shall see how they are varying. Here, as H increases, that is the magnetizing field increases, it faces two types of critical magnetic field. They are called as lower critical field and upper critical field, mentioned as Hc1 and Hc2. Actually, the penetration to be started at H0 and ended at H0. It is not happening like that. Before it start at HC1 and ended at HC2. That is, they have two critical means. Once again for you, they have two critical magnetic field, HC1 lower critical field and HC2 upper critical field. The specimen is a perfect diamagnet, that is perfectly a superconductor below HC1. That is, the magnetic field is completely expelled. At HC1, magnetic flux begins to penetrate, that is not H1. After HC1, magnetic flux begins to penetrate the specimen and the penetrations of the flux continues until the upper critical magnetic field HC2. In between these two fields, that is HC1 and HC2, are called mixed state. We cannot say that it is in a superconducting state. Some examples for typical type 2 superconductors are niobium zirconium and niobium tin alloys. The applications for type 2 superconductors may be listed for your understanding. They are greatly practical interest because they can carry high current density. They are used for power transmission without any loss. And they are technologically more useful than the type 1 superconductor due to tolerations of high magnetic fields. As we studied something about a type 1 and type 2 superconductors, we shall consolidate these two for better understanding. See, this is for your understanding purpose. It is listed. That is, in details we can say the distinguish between the type 1 and the type 2 superconductor. In type 1 superconductor, as the critical field is reached, the entire specimens suddenly come to normal state. Simultaneously, the resistivity returns. Resistivity returns means before critical field there is no resistance. After critical field, resistance exists. Whereas in the type 2 superconductor, the transition from superconducting state to normal state gradually coming. For such superconductors, two types of critical magnetic fields are there. One is HC1 called lower critical field and another one is HC2 upper critical field. In between these two states are called mixed state. After HC2, it become a normal conductor. That means resistance there only exists. This is the major difference between them, type 1 and type 2 superconductor. In a nutshell, we can say that only two states are present in a type 1 superconductor. But in type 2 superconductor, three states are available. One is superconducting state, another one is mixed state, and the last one is normal conducting state. As we know something about superconductor, conductor, type 1 superconductor, type 2 superconductor, still the superconductor is classified on the basis of magnetic field. That is, they are called low temperature superconductor and high temperature superconductor. The low temperature superconductor, the transition temperature is very low, that means less than 30 Kelvin. Such superconductors are called low temperature superconductors. They are all known as elemental superconductors. These superconductors are not practically useful due to ultra low transition temperatures. To attain that much of low temperature is not easy. Whereas in the high temperature superconductor, it is greater than 30 Kelvin, that is its transition temperature is more than 30 Kelvin. In a superconductor, if the transition temperature is high, that is greater than 30 Kelvin, then it is called as high temperature superconductors. Earlier, it was believed that superconductivity was possible only in metal, but Muller and other scientists discovered that a high temperature superconductor is possible in ceramics too. We think that the ceramics are very good insulators, but it is not so that ceramics can act as a superconductor at high temperatures, high transition temperature, that is above 30 Kelvin. Uh, the Muller and its collaborator produced a particular type of ceramic material from a compound of barium and lanthanum copper oxidants, that is barium lanthanum copper oxide. These are a typical ceramics. This compound shows a superconducting property above 30 Kelvin. It was a major breakthrough in this field. After that, a large number of metal oxide compounds with a ranging of transition temperatures greater than 30 are reported. The yttrium, barium, copper oxide, they are usually called as 123 superconductors, whose transition temperatures around 30 Kelvin. Then these are all possible only by making some oxygen defect in the ones. This is possible and it is proved by the scientists. We don't think that in superconductor Cooper pairs are formed. Yes, it is sure. Superconductor is nothing but the formations of electron pairs. And we shall see that formations of Cooper pair in the separate class. Before that, you just note it down. Example for some high temperature superconductors. Lanthanum barium copper oxide, whose transition temperatures around 36 Kelvin. After that, yttrium barium copper oxide, this is named as 123 superconductor, whose transition temperatures 19 degree Kelvin. Then tellurium barium copper oxide, it produces transition temperatures 125 Kelvin. Next, mercury barium calcium copper oxide produce 133 degree Kelvins. Further, scientists are trying to bring the transition temperature nearly room temperature. We know that room temperature is around 28 to 30 degree Celsius. However, you know that 0 degree Celsius is equal to 0 degree Kelvin is equal to 273 degree. We know that 0 degree Kelvin is equal to minus 273 degree Celsius. In Kelvin scale, there is no negative. Only in Celsius scale, both the negative and positives are present. 0 degree Celsius means 273 degree Kelvin. We know familiarly that our normal temperature is 28 degree or 30 degrees Celsius. That is equal to 303 Kelvin. So scientists are trying to bring the transition temperatures around 303 degree Kelvin. If it is achieved, means there is no loss of electric energy. We can get the superconducting phenomena even in the room temperature itself. Next, the slide shows to you the principle used in the bullet trains. Why we come to this sections means so far we saw what is conductor, what is superconductor, type 1 superconductor, type 2 superconductor, low temperature superconductor, high temperature superconductor, and a lot of informations we saw. After that, we come to the application sections. The slide shows that a magnet is floating over a superconductor. Why? We studied in the type 1, type 2 superconductor analyzation. Below transition temperature or below critical field, all the superconductor will act as a perfect diamagnetic one. That is, a superconductor will act as a diamagnetic one at its superconducting nature. This is the basic and the main keynote while you are studying the superconductors. A superconductor will act as a diamagnetic one at its superconducting state. Here the round plate is in superconducting state. You just float a magnet over it. If you float a magnet over it means the magnet emits a magnetic flux towards the superconductor. But the superconductor is in superconducting state. It will reflect all the magnetic flux towards the magnet. As a result, the magnet float over the superconductor. This is called levitations or floating. This principle is used in bullet train. See, in the case of bullet train, superconducting magnets is placed at the bottom of the train. That is, the train has a superconducting magnet into its base. An aluminum guideway above which the train will be set float by magnetic levitation. That is, we are using iron rails for ordinary trains, but for bullet trains they are using the aluminum guideway. It is just below the trains, but two superconductors are fixed below the bottom side of a train. As we know well, in a magnet, same poles are repel each other. As the magnet, superconducting magnets are fixed at the bottom side of the train, the flux will be present. During the initial moment, the flux will cut the aluminum guidelines. As a result, what will happen? According to Faraday's law, whenever the magnetic flux are cut by a conductor, current is induced in the conductors. So, current is induced. The induced current also produce magnetic field because they are brothers and sisters. Wherever the magnetic field is present, there will be an electric field. Wherever the electric field is present, there will be a magnetic field. So, the produced magnetic field as well as the superconducting magnet present in the train are in same pole. They repel each other. As a result, the train is floating over the rails. As the train does not touch the rails, the rails does not give any resistance to the wheel of the bullet train. This is one reason to increase its speed. You may ask that one question, and the train is just floating, not moving. For propulsion, immediate over the aluminum track, a south pole is induced. By seeing the south pole, the north pole will try to move the south pole present in the rails. Before to reach that point, immediately the poles are transferred to north pole. Again the train is floating. So, train is floating and propulsion both that takes place by changing the poles of the magnet present in the aluminum guideways. The diagrammatic explanations may be suited to you. If you go through the diagram clearly, if you want further information, you please go through some YouTube channels that could be very useful to you. After that, we shall see one more application called cryotrons. The cryotrons is a switch. Here two superconductors are used. The one means the conductor named as A having low critical field than the coil B. That means B has greater critical magnetic field and A has lower critical magnetic field, both of them in superconducting state. These arrangements will act as a switch. If you don't mind, you just note it the principle for cryotron. The principle is any superconductor will lose its superconducting property when the magnetic field applied over is greater than the critical magnetic field. Once again I repeat, the superconducting property of any superconductor will disappear when the magnetic field applied is greater than its critical field. Suppose A has some critical magnetic field and B has some critical magnetic field. If the critical magnetic field of B is greater than the critical magnetic field of A, then A become normal conductor. The output will not be present. That is in off state. It can be explained. Let us consider a superconducting material A. As I said, A has low critical magnetic field compared to B. And the A is surrounded by another superconducting material B as shown in the figure. You just see B is wrapped over the superconductor A. As I said, let Hc1, that is Hc1, or you may mention as Hca of material be less critical field as compared to Hcb, that is critical magnetic field of coil. Initially, let the temperature of the whole system be below the transition temperature of the superconductors A and B. That is, the whole system is kept in low temperature. Low temperature means the critical, let A have transition temperatures around 9.5 Kelvin and B have 10.5 Kelvin, means you have to bring the temperatures around 8 Kelvin. That 8 is less than 9 and less than 10. If you maintain in these temperatures, both of them will act as a superconductor. You just imagine in these situations, both of them in superconducting state. Now at operating temperature, the magnetic field produced the material B may exceed the critical magnetic field of A. Hence the material A become normal conductor. That is, A become normal conductor, B become superconductor. Because as current going through the coil B, a magnetic field will be developed. As I said already, magnetic field and current are brothers and sisters. As the current is going in the coil B, it produces magnetic field. The produced magnetic field is, that is Hcb, is greater than the critical magnetic field of A. In clearly, let it be 0.02 Tesla be the produced magnetic field by the coil. If the critical magnetic field of them wire A is around 0.15 Tesla, means the magnetic field, critical magnetic field of the rod A is less than the critical magnetic field of the coil B. As the current passing through the coil, it develops some critical magnetic field. The field is greater than the critical magnetic field of the rod A. So the rod become normal conductor. Therefore, current in material A can be controlled by the current in the material B, and hence the system can act as a switching element. Once again, I like to cut short the information very sharply. A superconductor will lose its superconducting property when it is subjected to a magnetic field greater than its critical magnetic field. Here, two superconductors are used, named as A and B. Critical magnetic field of A is less than the critical magnetic field of the coil B. Once the current passing through the coil B means it will produce the magnetic field. If the field is greater than the critical magnetic field of the rod A, immediately the rod A become normal conductor even though it is in superconducting state. The last one is squad. It is a very precision instrument used to measure the very weak magnetic flux. Even the magnetic flux produced in our brain can be sensed very accurately. The squad means superconducting quantum interference device. It is an improved model of Josephson device. It has high efficiency, sensitivity and quick performance. It has two Josephson junctions. Before that, you try to know what is Josephson junctions. It is a full circle. The full circle is cut into half circle and they are joined together with the help of some insulating material, thin insulating material. Normally, when the conductors are separated by a insulating material, current cannot flow from one conductor to another conductor. But here it is not so like that. In the case of superconductor, in a superconductor, current can flow from one superconductor to another superconductor though they are separated by an insulating material. This is called Josephson junctions. So here two Josephson junctions are present in the case of scud. As I said, the scud is used to measure the very weak magnetic field accurately. It consists of superconducting ring which can have magnetic field of quanta values of flux between the two Josephson junctions. Suppose when the magnetic field is applied perpendicular to the plane of the ring, current is induced at the two Josephson junctions and produce interference pattern. The induced current flows around the ring so that the magnetic field in the ring can have the quanta values of flux which corresponds to the value of magnetic field applied. Therefore, squads are used to detect the variations in minute magnetic signals in terms of quanta flux. They are used as a storage device for magnetic flux. They are also used in the study of earthquakes sometimes. Removing the paramagnetic impurities, detections of magnetic signals from the brains and the heart. These are all very useful to study the status of heart and brains by comparing them magnetic flux measured from a normal person and a patient. By comparing the flux from a normal person and from a patient, the doctors can analyze the conditions of the heart and brains of a patient. So this is very useful instrument in the medicine as well as earth science. Thank you, dear students. We shall see in the next sessions. Bye. See you.